let's go ahead and get started on midterm review. Let's start with, actually, forget midterm review. Let's start on the homework. Okay, so going over that. So we consider the regularization technique dropout with hyperparameter P. So that's like the dropout rate, right? We discussed scaling at inference time, right? That is not at training time, but at inference time. Another name for inference time is prediction time. Yeah. Why do we need to scale? Anyone want to?
The layer that comes after is going to be expecting a sort of net magnitude of input, and if you don't, when you have all of the outputs coming in, they're all going to be squared and will
Right, so if we've got the dropout layer here, and that's a good description, that you're going to have this layer here, and at training time, we're dropping out certain of these, and so it's going to get some particular net magnitude here at training time. But as soon as we turn these all off at inference time, it would all of a sudden get bombarded with magnitude. And so we want to ensure that the net magnitude remains the same at training time as at inference time. Because we really want, as much as possible, everything to be the same, right? When we train, that's the same situation we have when we infer or we predict. Similar in many ways, I think, to the idea of if we are normalizing inputs, that we need to do the same exact normalization to our inference inputs that we do to our training inputs. And so what we were doing was at training time, at inference time, scale by, we want it to be smaller, and so 1 minus p, if we read through, would be the right thing to do, right? Another question is, can we do it at training time instead? Nick?
Yes.
Okay, yes. And what scaling factor would you use? So this is at inference time, and then this is an or, right? Not an and. Sorry, let's not do inference time and inference time again, because it's so easy to do that. Let's say, or training time.
You scale upward.
We would scale upward. So scale, I'm going to just say scale by to mean multiply by, and you tell me what the factor is, but we know we want it to be greater than 1.
It would be 1 over 1 minus b.
Yeah. Any arguments against that? So certainly in one case, if we had a 50% dropout rate, then we'd scale by 2 at training time. And let's just try another one. If we had a 1/3, then we'd scale by 3/2 and not 3. So that's good. Okay. So does that make sense? All right. Advantages or disadvantages? Any advantages of either one?
If you had
Jake.
you change the rate.
So at training time, we can change P dynamically. I guess change sort of means dynamic, but let's just throw it in there. Right? We might have a training regime, right, where over time, let's say this is epochs, we might adjust various hyperparameters. For example, what might we do to the learning rate over time? Yeah?
Decrease it.
Yeah, we'd probably decrease the learning rate, right? Sometimes actually people like increase and decrease and increase and decrease, but eventually we would want to be decreasing so that we're really settling into the shallowest part of whatever our objective function is, right? So we might have the learning rate, which might go down on some sort of a schedule. So how would we implement this? in Keras? Callback. When would we do this? We get after each epoch. Makes sense. Beginning or ending of each epoch, one or the other. Okay, so we could do the same thing with the dropout rate. So the dropout rate, we could, it's not as common to do this, but we could, and it's not even really clear whether we want to be increasing or decreasing. Maybe we want to be increasing so that as it's beginning to overtrain, we fight that with more regularization. Okay. Seems to make sense to me. So you can do this because you can, as P changes, you can exactly ensure that the magnitude of the next layer, the net magnitudes remain the same. You couldn't do that at inference time correctly. So I guess we call this an advantage for the training time. I can think of another advantage for one or the other of them.
So that, like, it keeps the forward pass when you're doing it at training time. It makes it so the forward pass at inference time is like just completely normal. You don't have to do anything.
Okay, so yeah, if you so just to make sure here, we're talking scaling at training time. We can change P dynamically. Scaling at training time means dropout layer at inference time is a no-op. And why is that a good thing?
It's simpler, right?
Okay, simpler.
Quicker.
Quicker matters. We might be running this on a phone, right? So quicker is good because the user's sitting there waiting for it. What else besides quicker? Does simpler mean?
Is he just code?
It could be. Well, you can imagine. There could be a special thing when it gets deployed that actually doesn't even make, that actually just drops out the dropout layer, so to speak, right? That it can actually just hook up the previous layer k-1 to layer k+1 directly. But I'm just thinking of something other than speed on my phone that I care about.
Like the computational intensity, like how much.
So why do I care about computational intensity? I know why. Because I don't want my pocket to get hot, right? By the way, just a hint, never put a 9-volt battery in your pocket with change. I learned this by so you don't want to get hot, but what else? What is that hot? Okay, let's stick to the phone for a moment. What do we care about?
You don't have a lot of memory?
Memory might be affected a little bit. What else do I not have a lot of on phone? Or have a limited amount of?
Like data?
Data, possibly? Say that again, louder. Battery, right? I often use my phone untethered. Okay? I may be unusual, but I don't think so. And so you run out of battery, and it matters a lot to using less battery, which is less computation, right? Which is less heat. Your battery lasts longer. You had another suggestion? The storage, okay. Yeah. Does that make sense? Yep.
What is NOO?
No op.
Okay.
No op. Yeah. So it comes, I think, from assembly language. Most assembly languages have a no op instruction. So, which does nothing, which seems kind of useless. I can remember in my compiler class, years and years and years ago, we were compiling, right? In many languages, there's a null statement. What is it in Python? Pass. So the guy on my team, we were working on this compiler together, he says, pass, the equivalent of this in the language we were compiling, should compile to no op. And I said, no, pass should compile to nothing. There's no reason we don't need this one for one. Anyway, I won the argument. Of course, it was faster, right? It ran even faster by doing nothing than by doing an instruction that does nothing. All right, the next part of this. Any questions on that? Does that all make sense? Any guesses on what Keras does? Has anyone done the assignment? You have. Didn't even look at the Keras code. Daniel?
I think it scales at training time.
I believe it does scale at training time, in fact, because if you look at the code, it's like if you're not in training time, it just returns the input. So it's sometimes called inverse dropout, I think. The original description of dropout had it done at inference time. Yeah.
So we said that scaling at train time would make inference faster, but couldn't you argue the other way around, scaling at inference time would make training faster?
Sure.
Which could be more valuable sometimes?
It could be, because, I mean, well, so if you have a really, popular is not quite the right word, but let's just say popular model. A model that's going to be useful and used a lot, one hopes you're going to be doing a lot more inference than you will training. If you're developing an application that you're going to then sell to customers, right, what you're doing is trading off the time you spend training, the time and money you spend training versus the time and money of your customers. So, but yeah, I can imagine if you have something where you just need a model to do a little bit of work, you're not going to be doing much inference compared to the amount of training, then sure, you might make another choice. All right, GANs, which we talked about on Wednesday. So we have a generator generating fakes and a discriminator that discriminates real objects from fake objects. We know that G and D has these rounds where we train one of them and then we train the other. So let's just go through one by one. D is given training instances from ground truth real objects with a label of 1 and for generated fake objects with a label of 0. True or false? That's right. 1, 2, 3. True. Yes, that is true. D is given training instances given pairs of objects, either one ground truth and one generated fake, or two ground truth objects. It would be hard to see how you could say true to both A and B, right? And so, in fact, B is not correct. When you're doing a round of training G is the generator, you need real objects. Yes or no? You don't need a real object because all you basically are trying to do is say, did I fool the discriminator? Right? If you did fool the discriminator, your loss is low. And if you didn't fool the discriminator, your loss is high. And you're going to backpropagate. Let's say backpropagate. So this is a forward pass. Backpropagate through the discriminator, which is locked. Okay, because we don't want to be tweaking the discriminator yet. And then into the generator, and it will make adjustments such that it is more likely to fool the discriminator. So A is true. C, B is false, C is false. D. Well, if we're not going to use ground truth object training G, and we weren't using it to train D, not clear what we'd be using it for. So yes, we're using it to train D, right? We feed D. All right, here's our neural net. And our Y hats coming out are real or fake. Actually, let's even put it this way. It's really the probability of real, right? That's a better way to describe that. So 0 to 1. And what we're feeding in as training instances are reals with a 1 and fakes with a 0. Right? Matched in the sense we have the same number of each of them. Do we do one real, one fake, one real, one fake, one real, one fake? Oh, that'd be a really bad idea. Do we do a batch of reals and then a batch of fakes? No, what do we do?
Reals and fakes.
Yeah, I mean, basically we grab a mini batch of reals and fakes. Half reals, half fakes? No. We need to randomly select from the unending streams of fakes and whatever our stream of reals is, 50% probability with each, right? So that the discriminator has no knowledge when it's coming in when it gets a mini batch, whether it's all reals, all fakes, or some combination.
But overall, you kind of want equal numbers.
Overall, you want equal numbers. Yeah. If you don't have equal numbers, right, this is a general problem with neural nets, right? If you have one thing that comes in 1 out of 100 times, and the other thing comes in 99 out of 100 times, then the neural network can very quickly get 99% accuracy. Right? Just guess, it's the most common thing. And that's 99% accuracy already. Okay, back propagating. If we have the loss function L sub g, right, we have two different loss functions because we are optimizing two different networks. Do we back propagate errors from LG to weights in D? That is, we have G, which is a neural net, whose output feeds into D, which is a neural net, and that feeds into a loss function L sub G, right? So when we do our forward pass, we have to do a forward pass here and a forward pass here, right? When we do a backward pass from here, we know we want to change the weights in here. Do we go through this neural network? Excellent. So we can have a cage match between this guy and this guy. So why no?
Because we just want to see how well the generator did with respect to predictions he made. So we don't mind what's happening inside D.
Okay. Here's my question though. How are we going to get, we want the partial derivative of L sub G. Would you agree with this? With the partial derivative of the weights in G. Because how else will we know how to tweak these weights? Sorry, I'm not arguing for this. Go ahead.
We have to go through D to calculate those derivatives because the forward pass goes through D. So the backward pass derivatives have to go through D.
Yeah, this depends on these weights. And the way it depends on these weights is this complicated function that goes through here that includes this big function. So we have to backward propagate through this big function.
All right, but we didn't change the weights in D.
But we don't update the weights. Yeah, lock, 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 you know, frozen, 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 and then update, update, update. That's a crucial distinction. We go through it, we don't update the weights. If we're going from L sub D, do we do anything with G? No, because if we're going, right, there's a different loss function, L sub D. And L sub D, we have our inputs, either the inputs from here or the inputs from the real. And in any case, when you want to back propagate from L sub D to theta sub D, we don't have to go back any farther. We already have the inputs. Any questions on that? So it's, let me see if I get this right. True, false, false, true, false, false. False, so true, false, false. There are two truths, A and D. Is that correct? E, we do not back propagate the errors from L sub G to the weights. This is the key word here, to the weights. Do we have to back propagate to the activations? Right? To the outputs in here. Do we have to propagate to the Z, these Z's and A's? Yes, we have to propagate to the Z's and A's and get our way through here. But we don't care about the weights because we're not trying to change them. Right? If we keep in mind, whenever we do back propagation, we propagate from a previous layer to the A, and then from the A to the Z, and then the Z to the A in the previous layer, and A, and so on. And we keep going. Those we use to get the values for the weights and the biases.
So when you say propagate errors from LG to weights in D, is that essentially asking, do we ever compute some dW, d something in D?
This is basically, are we ever calculating some weight or bias in D? And we're never calculating this.
Would we propagate it through?
Yeah. Yeah, I could see the argument for through. I don't quite know the best way to word it. So, okay. All right, any questions? I'm glad that we went through in more detail there. All right, so let's now go through review. Maybe we can just, I'll put a little outline of what we have covered. You can let me know what I'm missing and then tell me what you're interested in. So we had CNNs, where we discussed convolutions. Max and average pooling. Here we can maybe just throw in padding and stride. CNN architectures. VGG. What are some others? Inception and yeah. ResNet. And in order to talk about ResNet, we talk about residual networks. More generally, I'll just say skip connections. So skip connections where we go from one layer, not to the next layer, but to some layer in the future, some later layer. We have talked about some new regularization techniques. Dropout, batch norm. And then we've talked about let's say generative networks. Generative, I'm going to just say generative. And examples of the generative would include the GAN. And then we also had visualization. So heat map, right, where we can see what part of the image is the network most responding to create the class. Visualizing activations. Just say slash features. And adversarial, which is not really visualizing, but it was sort of in the same realm. We were using some of the same techniques. So adversarial images is what you looked at, but more generally it can be adversarial input. Can anyone think of anything I've missed?
Style transfer.
So that's part of our generative. That's a good point. So style transfer, because it sounds cool, neural style transfer. All right. What would you like me to go into more detail on? What do you have questions on? Jake. ResNet? Okay. So for the ResNet, the idea basically is we've got a layer here. And normally, the layers all go like this, right? One layer to the next layer to the next layer to the next layer. And in fact, the API that we've been using right now for Keras, what do? I think we create a sequential, and then we add layers to that sequential. That's all we can do, right? We present each layer one by one, and Keras hooks up the output of one layer to the input of the next, to the input of the next, and so on. So in order to do something like ResNet in Keras, we'd have to use a different API that allows us to hook things up differently. Well, let's look at this functionally for a moment. So if we call this, right, this is some sort of a, this doesn't really even need to be convolutional. This could work just as well in a general network as well. But we're computing some function here by doing some either convolution or weight matrix multiplication and then doing some activation. So let's call this entire function f sub 1. And this is f sub 2. In fact, we could put a line in here. F sub 1, f sub 2, f sub n. If we have x coming in here, what does this calculate? Right, if we use function composition, y hat equals f sub n of f sub n minus 1 of f sub n minus 2 of f sub 3 of f sub 2 of f sub 1 of x. Yes? However, there are two reasons we might consider these skip connections. One reason to consider a skip connection, that is to actually take, let's say, the x and skip, I don't know, let's just skip 2 of these. We'll come down into here, and we'll add a plus. Okay, so that's a modification. I guess we'll do that in a different color. So what comes out of here is originally f sub 2 of f sub 1 of x. Do you agree? What comes out after we put this connection is x, because that's here, plus, and I'll do it in purple, f2 of f1 of x. Does the calculation make sense? And in fact, if we were doing Keras using the other API, the functional API, this is basically how we'd write it. We can just kind of call layers as we want. I'm going to call layer f1 and apply f2 to it, and then maybe add that together with x originally, so that has the effect of skipping. So this is exactly how you would do this computation in this Keras functional API. Jack?
Why wouldn't it be just x instead of just x plus f2 of f1 of x?
Well, if we
We're skipping over it, I guess. Like, is it because we already have that trained or something?
the reason is, the key part is, in here, we have a plus. So let's think about this a second. If we didn't want this in here, we would get rid of it, and our architecture would be simpler. We need somehow for how am I going to describe this? So let's go back to the definition, residual. So residual network. The network is computing residuals. So it used to be this network was computing the transformation from x to f2 of f1 of x. Now we're saying instead, f1 of f2 of x is computing the difference between what we want the output to be and x, right? This is the difference between our desired output and x. So this is now a residual. That value, F3 and F4, is now going to compute a residual from that, right? Not from the original x, but from that. And then we'll have this succession of residuals. Think of it kind of as tweaks. So first, we're going to tweak the input a little bit by adding something to it. And then whatever we've got there, we're going to tweak by adding some more to it. And then go on and add some more to it and so on.
So what is the benefit of that? Like, why is it theoretically better, or why did it perform better than like VGG or something?
Yeah, so there are two reasons. Reason number one, it'd be nice if you could add more layers and still not screw up a network. Right? If I've got a VGG 19 and it trains really well and works fine, and I want to now make a VGG 21, it'd be nice if that would work. Would just work. It's like if 19 works, 21 will work. Okay? But it may be that VGG 19 works fine, and VGG 21, like VGG 19 may be exactly what we'd like. And adding 2 more layers is harder than just having 19 layers. So if we've got some VGG 19, let's say, we know it's a good architecture, it'll train well with ImageNet. If we now create a VGG 21 that is exactly like a VGG 19, but it adds 2 extra layers. Conceptually, it seems like, well, all the neural net would have to do was learn all the weights from here and just learn some weights that just feeds whatever this input is to the output here. Right? If it could easily feed whatever the input is, let's put 2 extra layers at the front just to make it simpler. Okay, so VGG 21 is going to look like that. VGG 19, 2 extra layers. So if it were easy for this to learn just to transform x coming in here should be x coming out here, and then we'll do the other 19 layers that we already have, then adding new layers wouldn't hurt. But as it turns out right now, adding new layers can hurt. It can make your accuracy lower and so on. Okay.
Why are we skipping over 2 layers in this case?
We could do 1. ResNet just happens to do 2, but it could be 1.
Wait, I'm still a little confused. You said if it was easy for it to learn that it should be x after those 2 extra layers that we added. Is that just learning what the equal would look like? I'm a little confused.
Yeah, if we could do something like this. We have layer 1, we have layer 2. If it could learn to just spit out x from layer 2 and train VGG 19 just like it would normally, that'd work well. Right?
But then what's the point of adding the layers if what goes in is what comes out?
I'm trying to think about it from the point of view of this. Because we know VGG 19 works very well. And what we'd like to be able to say is adding more layers doesn't hurt things. And so one way that adding more layers could not hurt things is if it just learned this is an identity, and then it learned the rest of it like it normally learned. That would be one thing that could learn with this architecture. Okay? But this is not that easy to learn. Learning an identity in a couple layers is not that easy, but it is easy with ResNets, yes.
I think when we were talking about it, we said that it's easier to learn like the 0 instead of the identity.
That's exactly what I'm going to say, which is it's easier if we go back to here and let's say these are the first 2 layers. How can I learn x coming in here and x going out here? All I have to learn is 0 coming out of here. There are a lot of ways to learn 0 coming out of here, right? One way, if these are ReLUs, As long as what comes out of the z of f2 is negative, then this will all be 0. There are a lot of other different ways, right? I could set my weights to all be, I could set my weights and biases to all be 0, and then I make sure what's coming out of here is 0, right? Out of the bottom part. And then the top part will give me the x, and I can keep on. Or there are a lot of other choices for weights and biases that will get me zeros as well. Yeah.
Usually, do you modify x to fit the shape of F2, F1, or do you modify F2, F1 in a way such that it's the same shape as x?
So that's a good question. If F1 and F2 are convolutional, and we've chosen things carefully such that they do match, we're okay. Otherwise, what we actually do is do a slight mapping of x so that it fits whatever this output is. It's a good question because we're doing this plus. It's a pointwise plus that assumes the shapes are the same. If the shapes are not the same, we don't quite have x. We have a modified x, basically just multiplying by a little weight matrix that will also need to be learned to get the correct shape. Okay. So that is just one conceptual reason why it was thought of for ResNets, was if I happen to make, this is maybe another way to think of it, how do I know exactly the right depth for my network? If I use a ResNet, if I overshoot it, it's not so bad, because it should be pretty easy for it to learn to just zero out things that aren't necessary. And then the second thing that the skip layers give us is, right, the other problem with deep networks. One problem with deep networks is we have a lot of parameters to learn. Another problem with deep networks is the loss, the gradient, as you go back farther and farther and farther and farther, often has one or two problems. One problem, vanishing gradient, and the other problem is exploding gradient. Okay? Exploding gradient we can solve. Basically, whenever we have an exploding gradient that it's getting too big, we can just, let's say, scale it down, clip it, or scale the whole thing down. If we clip it, we get rid of the bad directions that are too big, but we're ending up with a different total net direction than we had before. Or we can scale the whole thing down, so just shrink the magnitude, but keeping the same direction. Either one of those can work for dealing with the exploding gradient. But the vanishing gradient is harder. Every step you take, we have this potential for our gradient to get smaller. Okay, what are some ways in which the gradient can get smaller? We can have an activation function whose derivative is less than 1. Okay, I believe tan h, its maximum is half or a quarter, we'd have to look, but less than 1. So if we had a tan h, for instance, activation function for each of these, we know that our gradient is going to be cut down in half as we go through this layer. So therefore, if we have a ResNet 154, we have it cut down by 2 to the 154th, which turns out to be fairly large. Well, small. So we just wouldn't get the gradient back to the beginning. Instead, right, remember what we're doing is, we want the gradient from here to here. We take all possible paths. All possible paths from here to the loss, and sum up the gradient. If we add a bunch of these skip connections, so one here, and let's say to here, into here, then we know one path back to, let's say, F1, the weights in F1. One path is we bring the gradient from the loss in, and then this is a plus b, right? So the derivative with respect to a is just 1. So we're going to go up here and have a 1. And then we go over again and have a 1, and a 1, and a 1. And 1 has the nice property that it's neither exploding nor vanishing, right? So we're keeping the gradient as is until we can kind of cut in and say, oh, here, let's go through these. Does that make sense? Yeah.
For the back propagation, do you take every possible path through the skips, or like every total way you can possibly go backwards?
The algorithm we use is not path by path. The algorithm we use is basically calculate the gradients of this entire activations here, and then the gradients here, the gradients here, the gradients here, the gradients here. So when we're, for instance, at F4, we're going to be taking the gradients coming in. We're going to be using this plus sign, basically, which is going to be adding the gradient from here and the gradient from here. So it's, thank goodness, not an exponential operation of this. It's this dynamic programming approach, basically, where we're just building on our calculations. And it's just this straightforward backpropagation that's happening. Other questions?
Wait, so can I just clarify that really quick? So
Yeah.
were you saying that it can get rid of the vanishing gradient because there are so many possible paths to the backpropagation, and since the derivative is adding up all different paths, then it's unlikely that the gradient will vanish?
Not quite. What I was actually saying was we know there's one path where the multiplication of the gradients is 1. It's the skip connection. So if you take this skip connection, we know it's going to be a 1 multiplied by the gradient. And this, the gradient, the partial derivative from here to here is 1. And from here to here is 1 through those connections. So therefore, we can take basically highway shortcuts of 1s all the way until we get to right before our weights that we're interested in. And so this gives us one path that doesn't vanish. There may be many paths that don't vanish, but this gives us one that doesn't. Okay. Any other questions on ResNet? Okay. Next question. And we're going to reserve the last 5 minutes to do an evaluation and talk about the exam.
Can you just a really quick review of like no padding, half padding, full padding?
No padding, half padding, full pad. Yeah. Here's the way I think of it. Well, let me just do some pictures. So let's say we've got a 3x3. No padding says we can't, when we're aligning our 3x3, we can't go outside the bounds of our image. So here's no padding. So our image is going to get smaller. Half padding says we are going to put some padding around the edge, basically half as big as our convolution is. Right, so we've got a 3x3 convolution, and we'll put half of that, which is 1 pixel border, around the edge. Right, so that's half padding. Or, to be explicit, it's a padding of 1 because it's a 3x3. If it was a 5x5, half padding would be how many pixels on each side? 2. Yeah. One way to look at this is where's the center, right? Here, this is the center. Here, this is the center. So here, the center is inset from the edges of the original image, which is why it's getting smaller. Here, the center goes up exactly to the edge of the image, so it's going to be exactly the same size. Full padding says it's going to be purple too, because I only have 3 colors. we're going to basically do padding of whatever the size is minus 1. So in this case, 2. So that we have at least a 1 pixel overlap between our convolution and our image. So in this case, the image is going to get 4 by 4 bigger. Right? It's going to turn from a 5 by 5 to a 9 by 9 if we go all the way around. And in this case, the center is not in the image, right? The center is here. Right, that's a 3 by 3. Does that explain that? Yeah.
This part you're talking about right now, what is that case for?
And this is full.
So what size convolution?
This is a 3 by 3 convolution.
Okay.
It's the same convolution in all cases. It's a 3 by 3.
In this case, so now the image would become larger after the convolution. That's what we're going for.
It would turn from a 5 by 5 to a 9 by 9.
Oh, that's okay.
Do you usually pattern zeros or?
There are some often zeros. Let's just say most of the time zeros. What are other things that might make sense?
You could double the outside edges.
Yeah, you could just copy the outside edges. Another thing you could do is wrap around. So it's like if you ever played like Space Wars or something, or asteroids where you're going around, left goes to right, top goes to bottom.
In this case, I was just confused about with the augmentations, wouldn't it go to 7 by 7? Because now we're adding 1 on the sides.
I believe, and correct me if I'm wrong, we're adding 2 on the sides, right? No. So you were right. It's the centers that matter. So this would go to from a 5 by 5 to a, so the end image is 7 by 7. I was confused by reading these paddings. So end image is 7 by 7. Here the end image is 5 by 5. And here the end image is 3 by 3. Oh, you had a question?
I was just wondering with the dropout layers.
The dropout rate?
Yeah. So I was wondering if you scale the output of the dropout layer by 1 minus p, would that be the same as just scaling the weights of the next layer by 1 minus p?
At inference time. So yeah, that's an interesting point. At inference time, if you're scaling by 1 minus p, is that not equivalent to scaling all the weights of the next layer by 1 minus p? Sounds correct to me, yep. And so if that's the case, then you could scale at inference time for no cost. Yeah, good point. Next up.
Can you talk about the highlights of the inception network?
Sure.
Just like what we're supposed to take away from
Here's the main thing that you want to take away from inception. So there were a few parts about it. So one is that it was deeper than the previous networks. Okay, so that is one part. And the next was so it was deeper than previous networks. And yet it also had fewer parameters. They didn't have residual connections. So they had an odd technique of getting error down to the beginning layers. Anyone remember that?
They had multiple stages where they calculated.
Yeah, they had multiple outputs. Right? Basically, they had some network here, and then they had output. A little mini network with output. And then they had more layers, and then another mini layer with output. So this was like, say, output 1, output 2, and then they had finally up to 3. And they would basically be saying, hey, after 10 layers or so, can you come up with what the whatever the final output is? You know, what class this was, let's say. And then here, after 20 layers of whatever this is, can you come up with it? And then finally at the very end, can you come up with it? And so that allowed a way to kind of take some loss from here and push it down to those earlier layers. So it didn't have to go all the way. It was still going all the way through here, right? But in case it vanished through here, we got some output coming in here as well. This was really the only time this is seen. So no one uses this anymore. It was an interesting idea. Yeah.
Just kind of curious. Say you had a GPU so you could run like things in parallel. Could you be, like, say you pass output 1, could you be forward propagating the rest of the network at the same time as you're backward propagating that part of the network that you've already passed based on that?
Well, could you be backward propagating here while you're forward propagating here? Probably not. Right? The key about a GPU is it's single instruction, multiple data. And so the single instructions are doing the same thing. And second, it doesn't really help you because you still can't go any farther than here because you're waiting for the back propagation from up top before you can go any farther from here. Right? Because you sum up all of the gradients as you're going down. Okay. The other key.
This wasn't really so much helping with like speed or anything as it was just like making sure the error got.
Not with speed at all. It was just a way to try and get error down to here. You know, it's kind of hard because it's also saying, hey, you better be coming up with some features that are useful for classifying early, which maybe isn't what I'm going to say wanted to do, to the extent it has loss.
So for example, if we have an exception for like image detection and then we know that the image has a certain label, are we using that same label to like...
We're saying basically, here you're predicting a dog. How good is it? I mean, it's supposed to be a dog. How good is your prediction? Here, how good is your prediction? It's probably worse, but it's really a dog. Here, how good is your prediction? Right. So basically, we take the output at one layer, we feed it through a little bit of fully connected. Right. So we don't just directly take the output. We put a small little couple fully connected layers here, so it has a chance of getting the right class. And then the big thing that Inception did is this network within a network. Right? When you're designing a network, how do you know when you want a max pool versus a convolution? If you've gone a convolution, how big is it supposed to be? Right? It should be a 3x3 or a 5x5 or a 9x9. You know, who knows? And so the Inception says, don't you, the architect, decide that. Let the network decide it. Let the network decide what it actually wants at each layer. So each layer is composed of, so this is a layer, is composed of, we've got input coming in here, and we feed that into a 1x1, we feed that into a 3x3, we feed that into, I don't know where it's 5x5 or 7x7, this is approximate, and we feed that into a max pool. And then we concatenate these together. By concatenating, what I mean is we're going to have the same height and width coming out, and we'll have a set of these that are the 1x1 outputs. And then we'll have another set that are the 3x3 outputs. And then another set that are the 5x5, and another set that are the max pools. So that basically what can happen is, if the network decides, you know, at this particular layer, we got layers above, we got layer below, max pool is really, really useful, it's going to be starting to adjust these max pool weights in important ways. And if it doesn't care about these, right, it just doesn't even bother with these weights. When this goes to the next layer, it's going to be reading these guys and not reading these guys. are maybe to read mostly these guys and a little bit of this 3x3. This one 3x3 feature is handy. Does that make sense? So actually, really, when I say it's doing 1x1 or 3x3 or 5x5 or max pool, that's not really what it is. It's doing 1x1 and 3x3 and 5x5 and max pool. So the next layer can decide what of that it wants.
Is there like a fully connected layer for images?
Is there a fully connected layer for images?
Yeah, so usually like the fully connected layer we use are for like array of like elements. Right?
Well, we know we're still going to have a fully connected layer at the very end.
Yeah, so that's after like we like put all the weights into like an array of one dimension.
Yeah, we do need to flatten out. Let's say this is the last layer. Flatten it out, and then feed it into a fully connected layer to 1000 if we're doing ImageNet.
Is there like a comparable fully connected layer for like images that's like height by width by 3?
No. It's part of the reason for that is there's a lot of weights. So, no. And Inception doesn't have several fully connected layers at the end, like VGG did. If you remember when you did VGG 16 or 19, there were a couple fully connected layers, 4096, 4096, 1000, and like 90% of the weights, 90% of the parameters, were all in those last two layers. By getting rid of that, that's how ImageNet can have a deeper network, but still end up with fewer parameters than VGG.
For these networks, did they all reach their maximum accuracy? Like, was there a point where it was taking too long to train, or did they train as long as they could? So did they reach their maximum potential in these networks?
Well, Inception, for sure, because Inception was done at Google, and they throw machines at this. There are, this may be tangential to what you're asking, but there are, a year ago, I think there was a year ago, there are competitions of not what is the best accuracy you can get, let's say, on ImageNet, but what's the least amount of training you can, the fastest you can train, just overall wall clock speed, what's the fastest you can train ImageNet, for example? Or what's the fastest on small versions of the images? What's the least amount of compute time or compute power, right, which is different from wall clock time, right? So if I throw 100,000 machines and it only takes me 10 minutes, that's not as impressive as if we use one machine for an hour. So a lot of that, though, doesn't actually have to do with the architecture and has a lot more to do with exactly how they're training and what the hyperparameters are chosen and some things like that. Oh, and lowest cost was another one, actually. If you're just using, let's say, AWS. What's the cheapest you can train ImageNet on? And I think it was around $300, which is pretty impressive, and it was a lot more back when ImageNet was, back when, let's say, these were done. Other questions? And I am leaving out a little bit here about the fact, for instance, that if you have a 1x1, a 3x3, a 5x5, a max pool, right? How does max pool end up the same size? So there's actually some post-processing that gets done in the max pool in order to make this get back to the same size as the others. And similarly, you want to refer to the lecture for some slight more details. I'm giving you the big picture of the Inception right here.
For the GAN, I was confused. What actually is it put into the generator network? Is it just like random, or?
So originally it was just random. So that you basically have your G here, which is a neural network, and its input is, we call it Z, and Z is in some random distribution. Okay, so it's just the seed, if you kind of think of it that way. It's a random image generator, or it's a random generator, and this is the seed that it's using. In some cases, you can feed in more than just a random seed. You can, for instance, feed in Z and also maybe a house with sun and cornfield. And there are generators that are trained to not just generate a random image, generate an image conditioned on this text, such that it actually might spit out, you know, this is my, with some wavy grass, wavy corn, and the sun. So that might be what it spits out. And then the discriminator would get in not only this, but also the description, right? So it would get a pair of both the description of what's supposed to be generated plus generator, but often it's just random number.
And then it would get a real copy of the description, like a picture that matches.
So this would be the fake, right? So this is the two inputs, and then it also has some real an image and a description.
But the description may or may not be the same as the one that you generated.
No, this would just be, I've got you can think of it, for instance, right, you know how paintings have names? So you can imagine still life with eggplant and artichoke, right? And this spits out, I don't know, a Rembrandt and says, I like hip hop, you know? Like, it could learn, those are not good captions. They don't match the captions that are real. So it'd be a more complicated neural network for both generation and discriminating. And in fact, on Wednesday, we'll start talking about recurrent neural networks, the way we deal with text.
So does it always have a description and an image, or could it just be an image? Or is it like discriminating between?
The discriminator would want both the image and, because otherwise there's nothing that's pushing this to generate, it would generate a good image, but not an image that is of this. So the discriminator has to help verify that it is of this. Yeah.
So, just to, I see obviously how errors going in both directions between the fake and the description. Is the generator produce like, so we can give a general description to the generator of the type of images or fakes that we want it to create, but then it's also generating a description with that fake?
No. What I'm saying is, so that wasn't clear. I'm sorry. We feed in not only some random noise, we feed in a caption. So we say I want a house with sun and cornfield. And if I have random number 5, I get this picture like a kindergartner. That's me. And if I put in random number 18, it comes out with a Rembrandt, right? Or something, assuming that that matches the kind of stuff we have over here, the kind of reals we have. But no, it's a generator that is generating things conditioned on, based on the caption that we give it. So if I get a different caption, it gives me a different image back. That should match, or the discriminator will catch it out.
So the caption is not modified in this case?
So the caption is not modified. The caption comes into the so let's actually show this. I'm sorry. So caption goes in here along with Z. Out comes an image. D, our discriminator, gets the image plus this. Yep. And then comes out probability real. And it gets to use the image, it gets to use the caption, it gets to use whatever relationship there is between the image and the caption to determine whether this is reasonable or not. If our reals had random images with random different captions, then the discriminator wouldn't ever care about the relationship between these and these. It would just say, does this look like a real image, does this look like a real caption? But nothing about, does this caption look like it matches the image? But if these captions match these images, then it's in the discriminator's best interest to use that information in order to get better. We've got time for just a little more, maybe one more.
Could you go to a batch norm?
Batch norm, sure. So for each neuron's output, there exists a mean, just say mean, and a standard deviation. Right, as I look over successive inputs, any particular output of a particular neuron, we could look and say, hey, what's the mean and the standard deviation of the things that are coming out of that? Right? And the reason I'm saying each neuron is because I want to make it really clear when I'm talking about a batch norm layer, it is independently operating on each of the outputs of that layer. So here, we've got our batch norm layer. And we've got, let's say, this neuron. And that's feeding into all here, right? And so as we have a mini batch, the output of this neuron, there's a particular mini batch mean and standard deviation, right? We have 20 items in the mini batch. We calculate of those 20, what's the mean and standard deviation. As we're choosing different mini batches, we can get different means and standard deviations, right, depending on the randomness of the particular inputs we're getting. And the thought is that maintaining a stable mean and standard deviation makes it easier for the next layer, rather than having the mean and standard deviation just moving all over the place. So for a mini batch, there exists a mean for the mini batch and a standard deviation for the mini batch. So this is the mini batch. Necessarily, this is just moving all around. We want to normalize that. So we just say, okay, for every one of these outputs, we're going to, for every like a sub I, we're going to say that equals a sub I minus the mean of the batch divided by the standard deviation of the batch. So if we did this, it'd take the mean to 0 and the standard deviation to 1 for our mini batch, and do that for every mini batch. The problem is this next layer may not want this guy to be spitting out a mean of 0. It might like this to be a nice large number, a healthy number of 55, around 55, plus or minus a standard deviation of 10. And when I say it desires, I just mean kind of the gradient would push it towards that. So it might be pushing back to this layer, something that says increase these values. But unfortunately, the way this is written, we would say, I don't care. Next time we run through, you're going to still get a mean 0, standard deviation 1. And so then what we add is a way for the batch norm to learn what the desired mean and standard deviation is. So we have learned parameters. This is the batch norm. We learn 2 params for every neuron. The mean and the standard deviation. So basically we take our a sub I, we first scale it to 0 mean, 1 standard deviation, so a sub I minus the mean of the batch divided by standard deviation of the batch, and then we multiply by the learned batch norm, and we add in the mean batch norm.
So when you said for each neuron's output there exists a mean and a standard deviation, which ones are those?
All these guys,
Yeah. Where are those means and standard deviations in this equation? Is it u sub b and sigma sub b? Or
probably the simplest thing to do is just make this, let's say this is A at K. We'll just make these be vectors. So if we make this a vector, then automatically that means we have, for however many neurons we have one value for each of those. Does that help?
I think so.
So basically we take our activation, we take, really all this is doing is taking our previous activation, right? Whatever our input is, subtract the mean we calculated, divide by the standard deviation we calculated, multiply by our parameter that we have just sitting there that we'll update using gradient descent. Add this one. Yeah.
Should we also have like an epsilon term on the denominator there?
Sure. Yeah. We don't like dividing by 0.
So if you pick a really small batch size, this wouldn't be very effective necessarily, because like you would only have a good distribution. Or
Well, let's say we had a batch size of, I don't know, 2 or 3. It would still learn, so we would expect if we have such a small batch size that the mean and standard deviation are going to be more changing around, and this might be more important rather than less important, because this will provide this stability to ensure that what's coming out remains roughly the same from step. It'll remain identical if these don't change, and it will slowly change as these change. Okay. And then the one thing we got to remember is at inference time, we don't have these values. And so these we need to save an exponential moving average for inference time. Okay? So basically these will be constants at inference time. They will not depend on the batch that you're feeding in at inference time. Yeah.
what is the equation for exponential moving average?
Exponential moving average is like x equals some alpha x plus some value. Let's see, is that roughly right? Basically, this is the decay, right? It decays this. So we take the old x and we shrink it down by a bit. And then we add in, I think we have to have some beta times our new value.
So in this case, the value would be like the current batch you're on.
This would be this would be the current mean or standard deviation batch norm. This would be the saved standard deviation batch norm. Saved, not learned, just saved for inference time. All right. Here's what I'd like to do. Let me pass out both the midterm and I have a midterm of my own, the midterm evaluation form.